All right, so now that we have an understanding of how to find the area inside a polar curve, let's start talking about how to find the area between polar curves, or that is to say, to find the area that is shared between two polar curves. Now, to kind of go back and think about this for a second, when we were doing this with rectangular functions, let me just change that size a little bit. When we were doing this with rectangular functions, suppose we had a function that looked like this, and then our other function looked something like this, for example, and we were integrating this from, let's say this is our interval here, a to b, something like this. And when we were finding the area inside these curves, this wasn't that bad to do because really you could just find the area of the larger curve, if you will, and then subtract from it the area underneath the other function. So oftentimes you saw me write kind of like the integral of the higher function minus the lower function, if you will. So you saw me kind of work through and kind of think about and functions such as that. Unfortunately for us, that doesn't really work here because our curves are being defined by rotations. With polar functions, it's not as simple as just saying the higher function minus the lower function. Now, the formula, or our formulaic approach, I should say, is actually pretty straightforward. We are going to take the area of one polar inside a polar curve and subtract the smaller polar curve area. So the actual calculation or the actual calculus of it isn't too bad. The most difficult part for us is going to be to try to find which regions specifically or which intersecting regions we actually want to integrate. And that's going to require some visualization and just some thinking of the bounds. And so let's actually, I think the easiest way is actually honestly just look at some problems, to actually just look at some graphs, see where they're intersecting, and kind of determine the best approach for each. I've written out a couple of different steps, so if you want to pause the video right now and write these down, I've written a couple of steps. These aren't meant to be linear, but necessarily, but just some things for us to think about, namely finding intersection points, checking to see if there might be any symmetry in these polar functions where we might be able to leverage the fact that they are symmetric about a certain axis, for example, just to simplify the number of calculations we may want to do, or and also to consider that we can have our calculators to help us trace the function and see what our limits of integration might be. And probably one of the biggest questions for us is to ask ourselves, is all the area accounted for? A lot of times we're going to want to look at the area inside a curve and then find that we've actually missed a particular area, or we might have actually counted that area twice. So these are all things that we want to consider. So like I said, let's jump right into a problem. We're going to find the area between r is equal to -6 cosine theta and r is equal to 2 minus 2 cosine theta. I encourage you to pause the video real quick, punch that into your graphing calculator. I went ahead and I also, right here, just gave an example of what your window would look like if you were writing this in degrees, if this was in degrees. So just to consider, if this were in degrees, you'd want to make sure that you have it as such. And like I said in my previous video, degrees are often nicer a lot of times just because it allows us to trace a little bit more easily with nice integer values. Okay, so go ahead and graph that. And after you're done graphing it, you should see that you have a circle, which is the first polar function, which is what I've highlighted in blue, and a cardioid for the second, which is what I've highlighted in red. And the colors are actually going to be kind of important in this lesson. So when I'm finding the area between these two curves, I'm effectively finding the intersecting or the overlapping region, if you will. And so I'm just going to quickly color that just so you can kind of see what I'm talking about. And so this is the entire region that I'm referring to here. This is the entire region here. And I'm just going to lightly sketch this, and I'm not trying to be very specific here, but this region that's inside the circle but also inside the cardioid is the region that I'm referring to. Initially, I had shaded just the top half that was above the x-axis because that can also help us out a bit, where we could see that this region is symmetric about our x-axis. So simply finding the region of finding the area of the region above the x-axis, we can then just double it to find the entire region. So probably a really good place to start with this is to first go ahead and find any intersection points. I'll write that. So intersection points. Where are my polar functions intersecting. So if you look at my if you watch my 9.2 video, we covered this towards the end of that lesson, because some interesting things are going to pop up when we compare what we get algebraically with what our calculator is telling us. So to find the intersection points, we're going to set our polar functions equal to each other. So we got -6 cosine theta is equal to 2 minus 2 cosine theta. And here that would just give us -4 cosine theta is equal to 2. Cosine theta is equal to -1/2. And so what are the angles of theta that cause cosine to give us -1/2? Well, that would be at 2 pi over 3 and 4 pi over 3. So algebraically, we have found the values for which these two graphs are going to intersect. And we actually only need theta, but I am going to actually write down the coordinates just for a second, just because I want to make sure that we understand something pretty important that's going to ultimately come up. So when I plug in 2 pi over 3, the first angle, into any one of my two polar functions, let's say, for example, my first polar function, -6 cosine theta, we would see that cosine of 2 pi over 3, so let me write this. This is going to be r is equal to -6 times cosine of 2 pi over 3, which is going to be -6 times -1/2. So we get 3. So what that means is this value here, or this coordinate, I should say, 3 comma 2 pi over 3, that represents a polar coordinate here. And we can actually identify that as this one right over here. It's 3, 2 pi over 3. And if we do the same with 4 pi over 3, we should also get 3 comma 4 pi over 3. By plugging in the values of theta into either one of the polar functions, we get the 2 points of intersection. And this would be 3, 4 pi over 3. Okay, so algebraically, we get this nice and easily. Now, in my previous video, I also discussed how to do this in a calculator. So I want to actually walk you through it, just kind of over this lesson, because I know that oftentimes in practice, we're going to be using our calculators to do this. The intersection method is the most precise way of finding these, the algebraic method is going to be the most precise way of finding these intersection points, but I recognize that realistically we're going to be using our calculator, so I want to make sure I want to clarify a few quick things. So on your calculator, once you've graphed them and you ensure that you're in degree mode, go ahead and hit the trace button. And if you do that, then I'm going to just switch really quickly to, let's say, degree. If you do that, your cursor is actually going to start right over here, or your little blinker or a little spider, as whatever you want to call it, is going to start blinking in that spot, because that's where the polar function starts graphing. When theta is equal to 0, we see that our r value here will be 6. When theta is equal to 0, r is going to be equal to, actually, -6. Excuse me. So when theta is equal to 0, r is equal to -6, which is why it starts right over there. And as theta starts increasing, if you hit the right arrow key on your calculator, you're going to notice that your cursor is going to actually start moving counterclockwise around your circle. But notice something interesting. When your cursor gets to this point right over here, when your cursor gets there, notice the angle that it's telling you. It's going to tell you that that is theta is equal to, if you're in degrees, it's going to say that it's 60 degrees, or pi over 3. To be very clear, 60 degrees is not a point of intersection. And that's probably something that's going to be confusing at first, because on our graph, what we're seeing here, it clearly looks like it is a point of intersection. But when we compare it to what we found here, when we compare it to what we found by algebraically finding those points of intersection, we don't see a pi over 3. Well, why is that? And I touched upon this in my previous video again, but it has to do with the fact that the point of intersection is not just the angle, but the entire coordinate, where that is true for both polar functions. So when we plug in 2 pi over 3, regardless of whether or not we plugged it into our circle or whether or not we plugged it into our cardioid, we got the same r value. However, if you try plugging in pi over 3 into your first function, so let me just quickly write this out. R is equal to -6 times cosine of pi over 3. Well, what does that give us? That gives us -6 times cosine of pi over 3, which is 1/2, which is -3. When you go ahead and try plugging pi over 3 into our cardioid, 2 minus 2 times cosine of pi over 3. Well, what does that give us? Well, that's 2 minus 2 times 1/2, which is 1. So we're seeing that the angle pi over 3 is giving us different r values. So again, to reiterate, although it visually may look like a point of intersection, we see that it is not actually a point of intersection. Those two polar functions are getting at the value here at different angles. So theta, when it's equal to pi over 3, is giving me a different r value for one polar function as it does the other. And a lot of that confusion has to do with the fact that we're trying to make sure we understand how these polar functions are built. They are, we're defining our curves based on rotations, okay? So hopefully that clears that up. And so we can kind of just state definitively, all right, so we know that our first point of intersection is going to actually be at cosine is 2 pi over 3. So when the graph goes all the way around, and let me actually keep this in green, it's going to go all the way around. Our first point of intersection is here at 2 pi over 3. And then it's actually going to loop all the way back around again. And when it hits 4 pi over 3, that's when it intersects with our cardioid. Now, if you want to see those points of intersection on your other graph, go ahead and hit the up arrow key and trace along this polar function. So if you hit the up arrow key on your calculator, you'll switch over to the cardioid. And here you can see, and I'll just do this in a different color, we're moving along this way here, along the cardioid, around there, okay? One thing you can also do is just to hit second trace and value, and then just put in something like 2 pi over 3, which we know is 120 degrees, and it'll place you right over here. If you then go ahead and switch, you'll see that 2 pi over 3, meaning you switch over to the other graph, 2 pi over 3 also places you at the same point on the cardioid. If you were to do that when theta was equal to 60 degrees, you'll notice that it places you down here, but if you switch to the other polar function, on the cardioid, 60 degrees is actually going to put you right around here. So those angles are not going to give you the same points of intersection. All right, so now that we have that, and I wanted to make sure I spent enough time on that because it's probably one of the most important steps. So now that we know that our points of intersection, and let me just go over that in purple, are there. This is probably the most challenging part for a lot of students, is to think of, okay, well, how do I actually want to set up my integral? What would seem to make the most sense here? And I encourage you to pause and think about this for a bit before watching what I'm about to do. So I'm going to switch to a different color here. I'm going to use maybe this color here because quite honestly, it just looks nice. The way I'm going to set up my integral is to say, all right, if I start at the pole and I start drawing sectors for my circle, starting where the pole is, and now remember, keep in mind where the pole is does not mean where theta is equal to 0. We know that when theta is equal to 0, we're actually over here. So we don't want to say that. But what is the value of theta that has our r value at 0? And again, you could do that by setting 0 is equal to -6 cosine theta, and see that cosine theta is equal to 0. Where does that happen? That's when theta is equal to pi over 2. So when theta is equal to pi over 2, so I'll just mark that here. When theta is equal to pi over 2, our r value is here at the pole. So we start at the pole. So starting from pi over 2, if I start integrating my circle from pi over 2 to 2 pi over 3, again, I'm going to start here and I'm going to move all the way out to 2 pi over 3, which is going to end right there. And integrating that is going to give me the area of this region here. And the reason why I want to stop there is because if I go beyond 2 pi over 3, now I'm drawing sectors out here. But this doesn't really help me that much find the area of my intersecting region. In order to do that, I would have to somehow find a way to subtract this area out here. But if I knew how to do that, then I most certainly would know how to do the area on the inside. So I'm going to stop at 2 pi over 3. Okay, so just again, be clear, I'm going to be shading in this region here. So I'm going to actually draw out the region that I'm going to be finding the area for. Okay, so I would say that the area of this region is the following. The area of that region that we just kind of highlighted there is 1/2 and the integral from pi over 2 to 2 pi over 3 of my function, my r function. We're integrating the part for the circle, so that's -6 cosine theta squared d theta. This is, again, just the area of a sector that we are integrating from pi over 2 to 2 pi over 3. So let me switch that over again. So from pi over 2, which is right here, to 2 pi over 3, which is right over there. And that's going to give me that region. Now, since I know that I'm going to need to find the entire region, so in other words, I'm going to need to also find this right here, really what I can just do is I can double that, since this polar function is symmetric over the x-axis. So I'm going to double this. So in other words, I'm going to say, I'm going to integrate, and this kind of looks like a little Pac-Man figure here. Congratulations, you can't unsee that now. So to find that region, I'm just going to take all of this and I'm going to multiply it by 2. I'm going to multiply all this by 2, which is often pretty nice because that just means we can multiply 2 times 1/2 and we're just integrating that. For the sake of time, I'm going to approximate my answer here. After I punch that into the calculator, you may want to check, make sure that you get the same thing as me. That's 1.6305. Okay. Now, what else is left over? What I also want to find now is this region here. Okay. So I want to start integrating now from there until I get to, and I'm just going to do this kind of drawing over exaggerated sectors here, all the way until I get to this. Okay. Now, notice now I am integrating along my cardioid. I'm now integrating along my second polar function, my cardioid. I know that that first point of intersection right here is at 2 pi over 3. And what we need to figure out is, where is this value right over here? What is theta there? And you can, again, use the trace feature, or you can also identify that it looks like there that r is equal to 4. Okay, so we can just solve that as well. We can say 4 is equal to 2 minus 2 cosine theta. So that's 2 is equal to -2 cosine theta. Cosine theta is equal to -1. And we know from that that theta then has to be equal to pi. That's the angle that makes cosine equal to -1. So that means this angle right over here is at pi. And that's going to represent our second bound. So we are going to integrate from 2 pi over 3 to pi for my cardioid. So what is that going to look like? That's going to look like this section right here. Actually, it does look like a sector. This section right over here, this is what I'm integrating. I'm integrating this using a bunch of little mini sectors, and that's the region that I'm integrating. So what does the area of that look like? Well, I'm now going to say, I'm just going to zoom in here, we're going to go 1/2 times the integral from 2 pi over 3 to pi over 2, and our polar function was 2 minus 2 cosine theta d theta. Don't forget to square that. And so that's going to give us the area of this sector here, okay, or this little section here. It's actually not quite a sector because I realize this distance isn't going to be the same as my radius there. But in any sense, well, remember, this too is symmetric. We also have this region down here that we want to find the area for. And so what we can do, just like we did in the previous part, is to just go ahead and double this. And when we go ahead and calculate that in our calculator, and also you could do this by hand as well, you should get approximately 14.0774. Okay, so that is just going to give us this bottom region here under the x-axis. So by doubling that, now I'm able to find the area underneath. Apologize for the messiness, right? This is now going to give us the area under in that bottom region there. We're then going to add those two sections together, and your final area of both of those should look something like 15.708 is what we're getting there. Okay. So there wasn't necessarily a step-by-step approach to this, but it did start with us trying to find the intersection. And again, we're probably going to be spending most of our time really focusing on our limits of integration, finding out where we want to integrate from, where do we start, and where do we want to integrate to. Let's do one more example. Let's take a look at this polar function, or these two polar functions. We've got a circle and we've got a cardioid. Now this problem is a little bit different because this time I want to find the area that is inside the circle but outside of the cardioid. So the result is this shaded region here that actually kind of looks like the hair for this dude with a receding hairline. But anyway, I just cursed myself. Now I'm going to have a receding hairline. All right, so we've got this region here. So first off, let's find the intersection points. Let's start with that. Intersection. Where are these two polar functions intersecting? Okay, well, we're going to set 3 sine theta equal to the other polar function, 1 plus sine theta. And let's see, that's going to give me 2 sine theta is equal to 1. So sine theta is equal to 1/2. So we can then say theta must be equal to pi over 6 and 5 pi over 6, if I'm not mistaken. All right. So again, you could use the trace feature on your calculator to see where those angles are happening, but you could also just plug in pi over 6 and 5 pi over 6 into your polar functions. And either one of those methods should see that this is going to be pi over 6. It's going to happen here. And 5 pi over 6 is going to represent this point out here. Okay, so where would we start here? So there are a couple of different options. There are a number of ways that you may want to go about doing this. I encourage you again to try to pause here and try to think about what would be the approach I would want to take to find the area in those shaded regions. Well, if you had a moment to think about that, one thing I do want to highlight before I proceed with this is also making sure that you know that pi over 2 is going to be this part right over here. That's where that r value is going to end. Well, for me, and again, you may have approached this a little bit differently, but for me, I want to start by finding this region here that I'm about to kind of mark up. Okay, so this region here, and let me just highlight this in this color. Okay, so this region here that I'm highlighting right now is what I would get when I integrate my circle, from pi over 6 to pi over 2. So when I integrate my circle from pi over 6 to pi over 2, this is what I would get. All right, something like that. So let's set that up. So this blue area that I'm finding here is the integral. So I'm going to say 1/2 pi over 6 to pi over 2. And my polar function was 3 sine theta. I'm going to square that, d theta. So that's going to give me that entire blue region there. Again, it's symmetric over that axis. So again, I'm going to go ahead and just multiply everything here by 2. All right. So let's not worry too much about the values. We can punch all that into our calculator in just a moment, but I just want to make sure that we understand what we're finding right now. The area, this enclosed region right now is what I have highlighted in blue, is my integral to the right. Then I'm going to need to subtract a smaller area to find the outside area here. So if I do this now in red, if I then go ahead and take my cardioid, and if I start integrating my cardioid here as such, kind of these lines kind of representing these sectors here. And what do we have here? Well, if I just go ahead and shade in this region, if I just go ahead and subtract this red shaded region here that I'm finding, well, if I take the blue region and I subtract the red region, then what's left over? It is this region up here, which I'll then just highlight here in purple. It would give us this area that I'm looking for, okay? And again, I'm going to be multiplying everything by 2, and that's going to help me take care of everything. I'm just shading in the half regions for now, but at the end you could just multiply everything by 2 and just double it and find it the same way. So we're going to say 1/2, and again, I'm going to have to multiply by 2, so might as well write it now. What were the bounds of integration there? Well, it's also from pi over 6. This is where we're starting, from pi over 6 all the way to pi over 2, and you want to confirm that you know that it's pi over 2 there and not a different angle because it was a different polar function, but you can just evaluate your polar functions there, just to make sure it does give me an r value of 2 for the cardioid. And this would be 1 plus sine theta That's squared d theta, okay? So by taking my blue region and subtracting the red region's area from that and making sure I double, because so far all I've done was half of it, then you could go ahead and you would see that your final answer, and these are actually pretty easy functions to integrate by hand, it's 3.14159. Hey, that looks familiar. Yeah, if you had done that by hand, you would see that it was exactly equal to pi. Now again, you might have done this differently. Some of you may want to just integrate and just say, wait, why would I want to stop at pi over 2 when I could just go from pi over 6 all the way to 5 pi over 6? That certainly is an option that is available to you. So you can most certainly do that. So in fact, I'll just write it out. Alternatively, you could have just said, let's find 1/2 the integral from pi over 6 to 5 pi over 6, right, of 3 sine theta squared minus 1 plus sine theta squared d theta. And that should also give you pi. And some of you are probably looking at that right now and be like, that's so much easier. I don't know why you had us doubling these half regions to begin with. Like I said, however it makes sense for you and however you can best visualize it.